what we have discussed already, and we got that the base wavelength was equal to, or 0, e to the h0 tau minus 1. And that's the base wavelength. Well, that's nice, because the star or whatever is a proper star, and it's moving property, and it is basically stationary relative to the distance that this thing goes. Now the thing is, though, sometimes I'll give an example. Sometimes that the galaxies, say this is a galaxy, not too good a drawing, but galaxies are spinning pools of stars, you might say. They are moving, and we could say this is proper motion. Okay, so here's a galaxy. The stars on this side may be moving in this direction. If they are, the stars on the other side are going the other way. Now these motions are peculiar relative to the proper motion of the galaxy. And if you look at Hubble's law, Hubble-Lamott's law, I should say, the motion of the proper galaxies is speed of light, whereas these stars have a relative velocity which is much less than that. However, it can be used as a method to find out information about the motion of stars and galaxies, and a big discovery was Vera Rubin found that these stars are all moving at the same speed, which is just contrary to what's expected in normal gravitation. But anyway, how does this work out in exponential expansion? Well, if we go with the same diagram, I'm going to do that diagram right here. If this is the original diagram, and let's say the detector's here, and this wave that's produced is moving in this direction. That's the direction of motion of the wave. I didn't spell that right, I don't care. Okay, so typically the wave would be here. Okay, we said that already, okay? Right up here. But what happens is that the emitter, the source, can be moving either toward or away from the direction of motion. If it's moving over a period of tau, if it's moving toward the detector, then this thing will end up here, and you'll get a shorter wavelength initially. The lambda 0 will be shorter. But if it's also possible that it'll be moving away, and I'm putting that here. And we have to consider also that this is an exponential movement. Well, after looking at the whole thing, you can see that if this thing is moving in this direction relative to the direction of motion, the new wave will be longer. This one, if the direction of motion, if it's moving in the direction of motion, if it's coming toward the detector, in other words, it will be shorter. If it's going away, so it's kind of consistent with redshift. Now, what does that mean as far as the detector? What is the general equation for that? Well, the general equation for that is going to be lambda. Okay, let me put some other things here. We would call this the original wavelength from here to here is lambda 0 prime. Now I primed that because this is the original lambda 0. I'm not doing anything with that. We're just observing what happens to the wavelength if the source is moving away. So this distance here is lambda 0 prime. Okay. Now, at the time it's produced, after the time it's produced, that lambda 0 prime will be moving at the speed of light toward the detector. Notice that the movement here of the peculiar motion is significantly less. It should be significantly less than lambda 0, because lambda 0 is moving at the speed of light, and this is somewhat less. Okay, so we can formulate an equation where it works out. You can do this. This is peculiar motion. E to the h 0. Now that, remember, this is the differentiable constant for the exponent, times 1, in this case, plus v0 over c0 times tau. And what that says is, you're adding this component exponentially, by the way, times tau minus 1. Okay, that's the different form of the initial wavelength. This is the initial wavelength when the source is moving, and the source is moving away, so this is plus v0 over z0. If it were less than that, it would be minus v0 over c0. But this is the form it takes. And what we do, it has an original wavelength of this, and it travels through space. Once this is lambda prime 0, so what is the detector getting? Let me move that up. The detector is going to get, this is the standard detector, is going to be getting a wavelength which started at this size, and it will, and that's lambda 0 prime. Okay, got a lot of primes in here, times e to the h0 delta t, and this is once again time of flight. So that's expanding too, but the initial wavelength is changed because of this motion. And you see, if these things are going around in a galaxy, this one over here is going in this direction. Relative to the proper motion, it's 0. So it's really, this term here goes to 0. There's no velocity in the direction of the proper expansion.